We're continuing with section 3.7 again, and we're about to start the chain rule. And to be able to explain the chain rule a little bit, it's important to go back to the example. Example 1, where Albert was running to be saved, and Pilot could tell the horizontal velocity of Albert, but he was interested in the vertical velocity. But Pilot would multiply the horizontal velocity by the slope of the hill to get the vertical velocity. And that was what we discussed over here as well. So there was the slope of the hill, which was the derivative of h with respect to x, and then the horizontal velocity, that was a derivative of x with respect to t, and Pilot would multiply them together and end up with the vertical velocity. Now let's go to chain rule, the chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function h equal to f of g, defined by h of x equal to f of g of x, is differentiable at x. And its derivative is h prime of x equal to, the formula comes now, f prime of g of x times g prime of x. Another way of explaining this is f prime at evaluated, so whatever f is, find f prime evaluated at the inside function, inside untouched, then multiply it by the derivative of inside. And so that's the formula of the derivative of composite functions. Another way of writing it, and this is very important in understanding a lot of material that comes later, is the Leibniz notation. So you take, and you saw that in the previous, in the Albert's example also. So if y is equal to f of u, and u is g of x, then derivative of y with respect to x is equal to derivative of y with respect to u times derivative of u with respect to x. So, and it is important when you're plugging in values though. Look, this one is f prime evaluated at g of x. So you're taking the derivative, but you're plugging in the inside function, and then you're multiplying it by g prime. And so one of the reasons the notation, the Leibniz notation, is interesting is that here it looks like things are canceling. They are not canceling. They're good enough for Calc 1, though in Calc 1 it looks like they're always canceling. Except we give you a couple of examples that you realize, oh, they're not really canceling. But this is an interesting notation, the Leibniz notation. They are not canceling. Okay, so let's do a few examples. Example 1. Find the derivative with respect to x of square root of x to the third plus x. So the first step to solve this problem is to figure out what's the inside and what is the outside function when you're taking the derivative. So in here I see that the square root is the outside function, square root of u is the outside function, and then I see u equal to x cubed plus 3 can make the inside function, right? And so g of x equal to x to the power 3 plus x is the inside function. And so write it out, y equal to f of u, and f of u is equal to square root of u is equal to g of x is x cubed plus x. Now, take the derivative of each function. So, derivative of f, or f prime of u, derivative of y with respect to u, or f prime of u, is derivative of square root of u with respect to u, which is, you can write it as u to power 1/2, then it's 1/2 u to power negative 1/2, which is 1 over 2 square root of 2. And then take the derivative of the other function, x to the third plus x, and that is 3x squared plus 1. Now apply the chain rule. So how you write it, write the chain rule, see the chain rule is dy dx is equal to dy du times du dx. So you found dy du, and then you found du dx, but dy d2 is in terms of u, and you want the end value to be in terms of x. So plug in what you're supposed to plug in, which is x to the third plus x. So that's the outside function. That's the derivative of outside function, and you plug in x to the third plus x. And then du dx is going to be right here, times 3x squared plus 1. So basically, we found the derivative of outside function, we plugged in the inside function unchanged, then we multiplied by derivative of inside function, and that's the chain rule. Chain rule is combined with other rules, and so other techniques also. This is an example. You see that there is a product rule. You're basically starting with product of 2x plus 3. Let's see, this is the first function, and that's the second function. So let's write the product rule first. And so derivative of the first factor times the second factor plus the first factor times the derivative of the second factor. Oh, sorry. And the second factor is x squared minus 1 to the power negative 2. Now, if you should notice, this is a chain rule and this is a chain rule. How come they are chain rule? Because there's an outside function here is to power 3, here is to power negative 2, and inside function. Inside function here is 2x plus 1, and in there is x squared minus 1. How do I find the derivative of this composite function? So outside function, we said u to power 3, right? So u to power 3, the outside function becomes 3 u to power 1 less. And so that's the derivative of outside function. But don't plug in u, plug in what u is, 2x plus 1. So basically, you took the derivative of the shell, the outside shell, and plugged in the inside function untouched. And then take the derivative of the inside function. What is the inside function? 2x plus 1, and so that gives you 2. Now, in here also, the outside function is u to power negative 2. So the derivative of that is negative 2. Instead of u, put a parenthesis to power negative 3. And then plug in the inside function unchanged. Then derivative of inside function, which is 2x. Now, when you write everything down, it's this times that plus this times that. And so here I write 3 times 2x plus 1 to power 2 times 2, make it 6. And then here x squared minus 1 to power negative 2 plus 2x plus 1 to power 3, times negative 2 times 2x. So I raise this, make minus 4. And so you have x squared minus 1 to power negative 3 times x. And so this is the derivative. So one way is to make it into a common denominator. So factor the lowest term, lowest exponent between there's a negative sign between them, right? That positive became negative because of that negative 2. And so lowest term of everything here is negative 3, lowest exponent of every factor. Negative 3 is the lowest of for x squared minus 1, and 2 is the lowest of 2x plus 1, and there's a 2 factor in common. So I do 2x plus 1 to power 2, and then x squared minus 1 to power negative 3. And what is left from the first bunch is 3, and x squared minus 1 to power negative 3 divided by x squared minus 1 to power negative 2 divided by x squared minus 1 to power negative 3 is x squared minus 1. So x squared minus 1, and here factoring it 2, there's another 2 left, and you have a 2x plus 1 and x left as well. And then when you clean this up, parentheses should close here. Basically, if you clean this part up, it's going to be 3x squared minus 3 minus 4x minus 2. 4x squared minus 2x. So that is minus x squared minus 2x minus 3. And rewriting that, you see that this is basically this becomes 2 times here, let's write the entire thing down now. It's 2 times 2x plus 1 to power 2 times this divided by x squared minus 1 to power 3, if I bring that to the denominator. So we cleaned up the factoring and we rewrote it, and this is what we end up with. This part was good enough for the gateway questions. Okay, so far what we've done is it could have been done by expanding the functions. I mean, not the first one, but the second one could have been done with the expanding of the function. And they, even if not that, they kind of look familiar. I mean, they are about the same. Type 1 and 2 look like it's some polynomial to a power, or a polynomial to a power times a polynomial to another power. Now we're doing the exponential with the exponent being different than x. What happens then? So in here you have the outside function is e to the u, and inside function, so y is equal to e to the u is equal to x over x squared plus 1. So derivative of dy du is just e to the u, e to the u itself. So basically, outside shell is e to the power, and that doesn't change. Then inside shell, du, derivative of inside is this one is a quotient rule, and it will be derivative of top times the bottom minus top minus the derivative of the bottom divided by this to power 2. It cleans up to x squared minus 2x squared plus 1, so it's minus x squared plus 1 over x squared plus 1 to power 2. So minus x squared plus 1 over x squared plus 1 to power 2. Last but not the least, we have the derivative of 9 to power 1 minus z to power 4. How do I do this? Again, what is the outside function? 9 to power u. Derivative of this y with respect to u is 9 to power u, natural log of 9. So that's what you write, and then du dz is going to be negative 4 z to power 3. And so it would be, the entire thing becomes 9 to power 1 minus z squared, which is u, natural log of 9, times negative 4 z to power 3. Parentheses closed. These are the side notes. That's the answer.